introduce you the next plenary speaker for this first session. It will be Professor Alberto Vomiero. He's chair professor in experimental physics at the Luleå University of Technology in Sweden, and his PhD was awarded in electronic engineering in the University of Trento. He obtained also the degree in physics from University of Padova, and his main interests are composite nanomaterials, wide bandgap semiconductors, semiconducting nanocrystals, and hybrid systems. And the talk today will be about composite nanostructures for high energy, for high efficiency excitonic solar cells.
Well, thank you very much for a kind introduction while we're waiting for the slides. And thank you very much to the organizers of the conference for giving me the opportunity of illustrating the results I obtained in my research in last years. Results have been produced essentially at CNR in Italy, and then in Canada at INRS, where I stayed a couple of years, and now in Luleå University of Technology in Sweden. Thank you. Great. So today I will be talking about the possibility of tuning nanomaterials properties for a specific application in solar energy, and mainly in solar cells, excitonic solar cells. Let me give you just a brief panoramic view of development in the field of solar cells. In the first, so-called the first generation solar cell was mainly based on single crystalline and polycrystalline silicon. One of the main issues on this generation of solar cells was the cost. They obtained roughly 20% of photoconversion efficiency, which is pretty good for the market, but it was pretty expensive. So the challenge for the community was to reduce the use of materials, to reduce essentially the costs. And then there was this second generation solar cells that was mainly based on amorphous silicon materials or other kinds of thin films, in which you significantly reduced the needed amount of material at the expense of the photoconversion efficiency. So you get around 7 to 12% photoconversion efficiency in the final panels, and this kind of cells can be found in some roofs. If you think to First Solar, it's a company which is commercializing cadmium telluride solar cells. They are very well positioned in the market. And then in a third step, people was trying to optimize the use of sunlight. Because in the first and second generation solar cells, essentially the concept was to use a single junction material with a very specific energy gap, so you can absorb just photons above the energy gap. What about the rest of the solar spectrum? So one of the main concepts to increase the photoconversion efficiency is the multi-junction concept, in which you use a cascade of materials with different energy gaps from the highest to the lowest energy gap, and you are able to divide the solar spectrum in different regions and efficiently absorb each of these regions. And up to now, the record efficiency for this kind of multi-junction cells is around 47% from Fraunhofer Institute, and of course it's pretty impressive that you can transduce half of the energy from sun power to electric power. Other different concepts derived in the third generation. One was about the concentrator system, in which you are using a mirror to concentrate the light in a very small and very efficient solar cell. This system is also effective, but the main problem here is that you have to follow with the sun with your solar system, so it's pretty expensive from a technological and engineering point of view. And then we have another kind of solar cells, the so-called excitonic solar cells, in which essentially you use different materials for the different parts of sun absorption and electric transduction. In this respect, we can see that different concepts can be applied for different kinds of applications. So for essentially, for satellite systems in which the cost is not a problem, they are typically using multi-junction solar cells. For portable electronics, you need to use flexible devices. For building integrated photovoltaics, the architects are asking you for semi-transparent and colored windows, as well as for off-grid applications. You need to use pretty cheap solar cells. Depending on the application you are targeting, typically you are applying different kinds of solar cells. And this is the scheme of the cost per watt in solar energy production. So in the first generation, the devices were pretty costly and pretty efficient. In the second generation, people tried to save money at the expense of the efficiency, and this is the real life. Well, this is, of course, the dream of scientists, having a very high photoconversion efficiency at no cost. Up to now, it's not possible, but we are trying to move in this direction, of course. So here you can see the scheme from NRL, in which yearly they update the certified record efficiency for different kinds of solar cells. And you can see that they span from above 45% to below 10%, because different kinds of solar cells target different photoconversion efficiency. So once again, depending on what you want to get, you can apply different schemes. And nanotechnology is helping us today in the sense that specific nanomaterials can target specific processes in solar energy conversion. In this respect today, I will speak mainly about this kind of solar cells. There are two main systems called excitonic solar cells. One is the dye-sensitized solar cells, another one is quantum dot sensitized solar cell. Respect to the single p-n junction solar cell, the nice thing in this system is that light absorption and charge transduction are carried out by two different or three different materials. So you have a dye molecule or a semicrystalline quantum dot that can absorb light, and then you create an exciton. Exciton is separated at the interface with a wide bandgap semiconductor, which is transducing electron, and then you have a Hall transporter of an electrolyte which can neutralize the dye or the quantum dot, and then you can start again the process. Unfortunately, you have these dashed arrows that are processes in which you are losing part of a charge that you have photogenerated. And people is trying to increase the photoconversion efficiency of a cell by fighting against these processes number 6, 7, and 8, and trying to collect all the photogenerated charges. And in this respect, I will show you today a few examples how to improve charge collection and photoconversion efficiency in some mixed systems composed of nanowires and nanoparticles and carbon nanotubes or graphene sheets, hierarchical structures in zinc oxide, and then I will illustrate you a few examples on exciton dynamics in quantum dots and in luminescent solar concentrators. So why nanowires are important? In these kind of solar cells, typically the electronic conduction is happening through hopping. And of course, after the generation of an electron, you have several thousands of hopping processes before being collected to the photoanode, to the front contact, sorry. in this process, you can lose a significant part of your photo-generated charge. So in 2005, Pedong Yang was suggesting to use single crystalline nanowires with much increased mean free path for electrons. And as Professor Morante was saying, nanowires have a pretty high surface to volume ratio, which is true for gas sensing, but it is not true for solar energy. If you compare the specific surface of nanowires compared to a mesoporous nanoparticle structure, it's at least 1 order of magnitude lower. So you can really transport very well the charge, but you cannot have the optical density you need to efficiently absorb the solar radiation. So what we tried to do is to grow our nanowires in different geometries and shapes. We can control the size and the length of nanowires. And then we wanted to test nanowires compared to a standard mesoporous system or a system which is composed by nanowires and nanoparticles. In this respect, you can have the high specific surface of nanoparticles and a very good electronic collection given by zinc oxide nanowires. If you look at the optical density of the system composed of nanowires plus nanoparticles compared to nanowires, you can see a significant increase in absorption, and this reflects directly on the short circuit photocurrent density in our solar cell and in the efficiency, which is almost 3 times higher than the efficiency with just nanowires. This kind of efficiency is pretty low because of the thickness of nanowires. We started as a proof of concept with nanowires with length of around 1.5 microns, while in this kind of cells the optimum thickness is around 10 to 15 microns, but the result was pretty clear, and in fact Professor Wang a few years later got around 7% efficiency with the same concept, but increasing the thickness of a nanowire layer. We tried another way to increase electron collection in titanium oxide nanoparticles by integrating graphene nanosheets or carbon nanotubes, and in this process we tried to increase the conductivity of our layer and to decrease the recombination processes. The idea was preliminarily drafted in 2008 by Professor Kamat, and he was very negative in the outcomes of this system, because what he did, he took a forest of carbon nanotubes, he covered with titanium oxide nanoparticles, and then he tried to test the solar cell, and as you can see here, he got an increase in photocurrent density, but a significant decrease in open circuit photovoltage. So essentially, the photoconversion efficiency was not increased at all, and his conclusion was that the system doesn't work. So we said, okay, but probably the idea of increasing the collection of charges is good. So let's try to reshape the idea of Professor Kamat. And what we did is not to use a nanoforest of carbon nanotubes, but just a very, very small concentration of them. And you can see that by using this small concentration of carbon nanotubes, we were able to go from 6.5 to 8.1 photoconversion efficiency, and in the optimized system from 7 to 9%, which was pretty good for us, this kind of increase in these cells. What's the difference compared to Kamat's work? It's exactly the concentration of carbon nanotubes you have in your system. And in fact, the maximum efficiency is just for 0.01 in weight carbon nanotubes in titanium oxide. If you look at the previous results were employing much higher concentration of carbon materials. And in this part, as you can see, you lose all the effect of the beneficial effect of carbon materials in boosting the functional properties of a device. Why it didn't work at higher concentration. First, one of motivations is that carbon nanotubes and graphene are absorbing light which cannot be used for charge photogeneration. And secondly, because at higher concentration you have the formation of cracks in the film, which is no more suitable for charge transport. We got the same with graphene nanosheets. People was not believing us that graphene was still in the system after high temperature annealing at 500 degrees. So we applied two-dimensional micro-Raman to get a clear picture of graphene sheets after integration into titanium oxide layer. And we got almost the same results as carbon nanotubes, so from 6.3 to around 9% photoconversion efficiency. However, we were surprised because if you look at the distribution of titanium of graphene platelets, which is these blue dots, the best sample is this one. So the main idea was to create connecting network inside titanium oxide for transporting charges, which is not the case. Graphene concentration is well below the percolation threshold. So our idea was that, and we tested by trying to focus at the different depth in the film, that graphene is mainly concentrated at the interface between titanium oxide and the conducting glass. So its effect is not just to transport the charges, but to fasten and to increase the charge injection from the titanium oxide and the front contact of our solar cell. Another example on how to manipulate nanomaterials is the case of zinc oxide hierarchical structures. In this case, we capitalized on this kind of micro beads that are composed of very small nanoparticles. And this system is very intriguing and interesting because it has a very high specific surface given by the nanoparticles, and at the same time the large dimensions of grains make the system a highly scattering one. So you can have sort of Anderson localization of light inside your system, which is highly scattering, and you can increase the probability of light absorption when your photon is confined in your solar cells. And we tried to get these kind of systems through a very simple process of sprite deposition, and we also applied a pretty thick buffer layer of zinc oxide to inhibit the back reaction from the conducting glass and the electrolyte. And the results were pretty nice because we were able to get these kind of microstructures that are composed of very small nanoparticles. It's still not clear why under annealing these kind of large crystals are forming these hierarchical structures during the firing process, as you can see here. But it's highly reproducible, and we are trying to investigate such a process. Of course, this is not a nice material from the, let's say, a transmission electron microscope point of view, but it works. And it works pretty well. We got 7.5% photoconversion efficiency, which is the highest for zinc oxide-based dye-sensitized solar cells. And we were also very happy to identify very clearly the effect of the buffer layer. You can see here without buffer layer and with buffer layer, and this is the electronic electron lifetime in our system, which is significantly increased due to the inhibition of a back reaction from the conducting glass to the photoanode. And then let me move to quantum dots. So the first part was about oxides, which is the part which is targeting electron transport. Now quantum dots relate with light absorption and exciton generation. Why quantum dots can be interesting for solar cells? Well, the debate is still very open. Nice thing in quantum dots is that you can modulate the energy gap by simply tuning the size of your particles. You can claim that there are intraband transitions in your system, so you can absorb 2 low energy photons to get 1 electron produced, while in other materials, if you don't have such kind of bands, the low energy photon is lost. And then people is also claiming the possibility of so-called multiple exciton generation, in the sense that you can absorb a single energy photon, and then the relaxation of an electron, of a high energy electron, gives rise to formation of a second electron. So you can get more than 1 electron for single photon. And this process is pretty clear from the theoretical point of view. There are some also experimental evidences, but the scientific community has not yet accepted probably this one. But luckily I'm not working on MEG, so I can go safely ahead. One of the interesting points is that when you change the size, you change the energy gap, so you change the color of your quantum dot, and you can absorb different parts of the solar spectrum. The problem is not only to absorb light, but how to proceed once you have these electrons produced, and how can you inject electrons from the quantum dot to your titanium oxide system, or zinc oxide, or tin oxide, or whatever it is. An interesting point was to monitor during the lifetime of photoluminescence of these quantum dots. And it was proposed for the first time by Konganad and Hamat for quantum dots, cadmium selenide and cadmium sulfide, which are active in the visible. And they indeed showed that different size of the quantum dots result in different injection rate from the quantum dot to titanium oxide. And typically, the larger is the quantum dot, so the smaller is the energy gap, the slower is the process of electron injection, because the electronic states of the quantum dots are pretty close to the one of the titanium oxide conduction band. So we tried to do the same with quantum dots that were active in the near infrared region of a spectrum, which is interesting because it's typically lost as a heat in solar cells. And you can see here with a hot injection technique, you can pretty nicely tailor the size and the excitonic absorption of the quantum dots, and also the photoluminescence and the peak position. And then what we tried for the specific application of solar cells was to investigate the rate of electron injection from the quantum dot to titanium oxide or to tin oxide. We have chosen titanium and tin oxide because they have a pretty different positioning of conduction band. So you expect that the transfer rate is critically dependent on these two positions. And of course, for such sizes of quantum dots, the injection is absolutely forbidden, while for others is can take place. What we did was to monitor the photoluminescence lifetime in different systems. We used silica particles, the black line, as a benchmarking system in which you have no electron transfer from the quantum dot to silica particles. So, and of course it has the longest lifetime. As you can see here, injection to titanium oxide, which is the red dots, has a a longer lifetime compared to tin oxide, as we expect if you look here, because this is titanium oxide, this is tin oxide, so I expect a much faster and favored injection into tin oxide, and we proved it. And of course, if you change the size of quantum dots and you increase it, you inhibit the charge injection. And the same is when you use some protecting shell, because this kind of system, especially the lead sulfides one, are suffering surface oxidation. So we covered with a few monolayers of cadmium sulfide, and as you can see here, if the shell is too thick, you inhibit the charge transfer. So it's possible to play with size and shell protection to get a good electron injection from the quantum dot to the oxide. Let me now move to the last part, which is connected to quantum dots, and it's the so-called giant quantum dots or dot in bulk systems. The inspiration came from the work of Professor Klimov, and who for the first time proposed these materials in which you have a quantum confined system in the core of your structure, surrounded by pretty thick shell. And the thick shell has a classical behavior from the optical point of view, while the core is still a quantum system. So you can have essentially a two-color system in which you can tune the properties of the emission of two different parts. And we did the same with the systems that are optically active in the near infrared region. So we used a core of lead sulfide covered by cadmium sulfide, pretty thick shell. So production and size distribution is pretty straightforward to obtain, while it's not so clear what's the structure of this particle. Typically in literature, these kind of particles are supposed to be spherical. We demonstrated that they are not spherical at all. And while typically we identified a zinc blend structure which is surrounding the core, and then you have a Wurtzite structure which is growing outside the zinc blend structure. So it's not at all a core shell. And probably since the luminescence comes from the Wurtzite and from the core, this special separation of the two regions can affect the ability of the system to keep the two optical properties separated, because there is less communication between electrons from the core and the shell than in a standard core shell structure. Of course, phase identification through XRD was almost impossible in the core shell system due to the overlap. And we tried to get some optical characterization of the system, as you can see here. For the proper thickness of the shell, we got a visible emission and an infrared emission. And the main explanation of this through time-resolved ultrafast techniques, I'm not expert at all on that, is that while you have quite high delocalization of electrons through all the structure, the holes are pretty confined either in the core or in the shell, and they cannot communicate each other. So you can have de-excitation according to the specific wavelengths of the two systems. We tried to apply these quantum dots to luminescent solar concentrators that are semi-transparent windows in which you can collect the re-emission of your quantum dots in the side of your window, and you can put a solar cell, a very small solar cell there. And the nice property of these quantum dots is that when you use properly the thickness of a shell, you can significantly increase the Stokes shift of the system, which is very nice for luminescent solar concentrators, because what you get if you don't have a very large stock shift is that you have a reabsorption processes of quantum dots that reabsorb the emitted light, while if you have a very large stock shift, essentially the light can travel once it's produced without being reabsorbed here, as you can see. And it was pretty nice, and we got one of the highest efficiency for this system. Just a couple of seconds to say that these two different color emissions are temperature dependent. So by changing the temperature, you can change the color of your nanocrystals. And this is very interesting because you can get autonomous temperature sensor with one of the highest sensitivities in literature. And that's it. I hope I've convinced you that by tuning the properties of both oxides and quantum dots, we can increase the photoconversion efficiency of these solar cells. They are not still in the market. Probably we can search for other directions where to go because, yes, they're pretty challenging and the stability is still an open issue. Let me acknowledge all people working with me to get these results. I'm now associate editor of Nano Energy, and we are trying to collect good papers on nanomaterials for energy. And thank you very much for your kind attention.
Thank you very much, Alberto, for this very, very interesting talk. Now it's time for questions. Maybe we have. Yeah. Yes.
Oh, very nice talk.
Thank you.
Regarding the alternative that involved using carbon nanotubes, you mentioned that you start with a forest of carbon nanotubes. You also said you pinpointed the concentration and you started changing that. So my question is, if you were to not only play with the concentration, but also the way the carbon nanotubes are, so say you grow them straight up in a grid so that they don't interact, do you think that's something worth exploring, or you think you'll have the same effect?
No, it can be explored, and I mean, concentration is very critical. If you look at some SEM pictures, the problem with quantum dots, the carbon nanotubes, is to detect them because they are conformally covered by nanoparticles. So essentially, they're embedded in the matrix. If the concentration is pretty low, there is absolutely not a problem in having these mats of carbon nanotubes all together. So it's absolutely something that can be explored. And one way to do it, for instance, is to functionalize the carbon nanotubes. If you have functionalized carbon nanotubes, they're very well separated. They can stay in your solution for several weeks without any detrimental aggregation. So.
Yeah, I have a colleague who functionalized the surface and put them into a nanofluid, but his final conclusion was that the scale up to get any workable solar cell would be almost impossible. You'd need a football field solar cell just to get the...
Well, if you want to use them as probably light absorbers, yes, but
yeah.
As electron transducers, they can work well. Right. Thank you.
Maybe one more question? Not. I have a question. Did you ever try to use any plasmonic system in order to enhance the energy harvesting? No, now it's working.
Okay. Yeah. No, I was yesterday with Professor Pastoriza. I was asking her, can you collaborate with that? Because no, in the plasmonic system, in this kind of solar cells, indeed, are pretty original. And yes, we want to try, but we have not yet tried up to now.
So, and it was good to have good contacts in the Congress.
Yeah.
So if there is no other question, we will move to the next talk.